All right, sorry for the delay. So today I'll talk about hidden Markov model. So helpfully, by leading you guys through the recitation, you guys will know how to apply some of the algorithms or methods you learn in graphical model to a real application. And here's the model. Here's the graphical model. First, we have the observations, x1 from x1 to xn. And we assume that for each observation, there is a latent variable, which is from z1 to zn. And the critical part is that we assume that this hidden variable, they follow a Markov chain, which means that the transition from z1 to z2 follows Markov property. And because of this is a Markov chain, so we have conditional independence in the graphical model, which means that given the variable zn, zn-1 and zn-2, zn-1 and zn+1, they are independent. So with this graphical model, we can also write out the joint distribution. So here's the prior of the first latent variable, and here's the transitions. This follows the Markov property. So zn only depends on zn-1, and the observed variable depends only on zn, xn depends only on zn. So this is a joint distribution. Because there are a lot of independence in the graphical model, and we will make use of this independence later on in all the algorithms, in all the derivations. So before doing that, we have to introduce some parameters. So we assume that there are k-state for the hidden variable. We assume that the hidden variable is discrete, which means that it can be in any one of the k-states. And because this is a Markov chain, we have to introduce the transition probability, which we denote by pzn condition on zn-1. And the transition probability is given by this transition matrix. And this transition matrix fully characterizes the Markov chain. And every entry in the transition matrix, ajk, means the probability of transition from state j to state k. And this is the whole transition matrix means. And also we need to have an initial probability for the first state, because this is the state we transit from nowhere. We have to specify the initial probability. And we also have the emission probability. This emission probability is a probability that x given z, which is that given the latent variable, what's the probability of the given the latent variable, which is what's the probability of the observed variable. And this distribution can be Gaussian, can be multinomial, can be anything. So the most important part in the hidden Markov chain, hidden Markov model, is that the latent variable, they are discrete. When they become continuous, it becomes another model, which is called Kalman filter. And the derivation is more complex. So we will focus on the case that the latent variable are discrete. So here's all the parameters. Pi is the initial probability of z1. A is the transition probability among the states. And phi is a parameter of the emission probability. It can be Gaussian, it can be multinomial. So having quantified all the probabilities, we can derive some quantities. But before doing that, I want to call your attention to some kind of relationship between hidden Markov chain and clustering. So remember that in the mixed Gaussian model, I will do a little bit review of the Gaussian mixed model. So in the Gaussian mixed model, there are several clusters. Each cluster means a Gaussian distribution. And assume that there are 3 clusters: cluster 1, cluster 2, cluster 3. This cluster denotes the Gaussian distribution. We say that the mean is mu1, covariance is sigma1, and for the second cluster, it's also Gaussian. the mean is mu2, sigma 2, and here mu3, sigma 3. This is Gaussian mixed model. And this Gaussian mixed model is also the underlying model of k-means clustering. So in this model, this is an unsupervised model. So we have to specify the way we generate the points. So this is how Gaussian mixed model generates points. First, we randomly pick one cluster according to some prior distribution. And once we pick one cluster, which we pick one Gaussian distribution, then we draw 1 point from this Gaussian distribution. Assume that we pick this third cluster, and we draw 1 point from this Gaussian distribution. Assume that the point is here, and then we continue to generate some other points. And then we have 3 clusters. This is Gaussian mixed model. In the model, during the process we pick the cluster, it's independent of the previous state, which means that at time t, at time n, say we pick the third cluster, then the next time we pick another cluster, the probability is independent of the scenario that we are actually in this cluster. So the probability that we pick any cluster is independent of the previous cluster that we are actually in. So this is the Gaussian mixed model. But hidden Markov model is more generous. It can characterize the case when the next cluster we pick depends on the previous cluster that we are in. So this is the difference between Gaussian mixture and the hidden Markov chain, hidden Markov model. So in other words, if we constrain that the conditional probability of transition to be independent of Zn, then the hidden Markov model becomes the Gaussian mixture model. So this is the relationship between clustering and the hidden Markov model. So in other words, we can also use hidden Markov model to do clustering. And we will show how you can do clustering later. So having specified all the quantities, all the probabilities, all the transitions, we can calculate some quantities that we want using some kind of algorithm that you learned before in the graphic model session. One quantity that we are interested in is the posterior probability of Zn given order of observations, which means we have seen order of observations. So we want to calculate the posterior probability that at time n, which state we are in. So by using Bayesian rule, we can write out the probability as this. And we can further expand this formula by making use of conditional independence. I will show you how. So since this constant is independent of Zn, so most of the case we ignore this constant. So this is a trick that we use very often in graphic models. So for this part, we can write it out, making use of conditional independence. First part, this is from x1 to xn. So we can write this term into the product term because they're conditional independent. So there are two terms here. We denote these two terms as alpha and beta. So we will show that this alpha and beta are the actual message that we passed to node Zn in the sum product algorithm. So in the sum product algorithm, we first convert the original Bayesian net to the factor graph. The original Bayesian net is like this: x1, z1 to z2, x2, zn, xn. So we can write out the joint probability distribution, which is z1 times x1 conditional z1. This is the first term, z2 conditional z1, then x2 conditional z2. So we group these two terms together. So we denote this as H. This is f2, and then we can just like this. So with this term, this is a term here, and then we have the first d1. So this is the original Bayesian net. This is the factor graph corresponding to the original Bayesian net. And the factors we are actually use here is by grouping, divided the original joint probability distribution into groups. So the total distribution is the product of all these factors. Now this graph becomes a chain. Then it becomes quite simple. We can make use of many properties of this chain to simplify many algorithms. The first is the sum product algorithm. We want to calculate out So we want to calculate out which is the marginal probability of Zn. So this is a node Zn that has, say, fm minus 1. Am I right? Just so we want to calculate the marginal probability of this variable. So we use the message passing algorithm. We pass that message from both ends. So from both ends. And we use of the sum product. So during the message passing, the product term is around the variable. So we have mu f which is directly equal to this is because for this variable, there's only one connection here. If there are several connections there, then we have to calculate the product of all these terms. But here, there's only one connection here. So this product, there's actually no product here. If there are many connections, then we have to calculate the product of all these terms. So for the sum calculation, oh, sorry. For the product term, we actually calculate all the sorts from this Fn because there's only one connection here. So we only use, so this product becomes directly equal. So for calculating the message to Zn, because this is a term, this is actually a term, function of Zn minus 1, Zn. So we have to calculate the summation over this Zn minus 1. So this is why we have the sum here. Because of this line structure, the sum product algorithm becomes quite simple. So for this node, Zn, the message from the left, we can denote this as alpha, and the message from the right, we can denote it as beta. Then the marginal probability is just the message from the left times the message from the right. So that's why we have this simple term here. And then we can use this marginal probability to calculate out the positive distribution. Because this px is constant, so the term that really matters is alpha and beta. And we can simply use the sum product algorithm, which is message passing, to calculate out the marginal probability very easily. So another quantity that we want to calculate out is the most probable state, which means that given these observed variables, which is the most probable state, which we can also use, say, cluster, which is the most probable cluster this observed variable belongs to. So how can we calculate this out? Note that the sum product algorithm is actually calculating out the summation. Here we are calculating the max, which is the main difference. But we all make use of the conditional independence during the process. So for the sum product algorithm, so we calculate out Z1 to Z n minus 1. But here we want to calculate the max. This is the summation. This is the max. Although there are some difference in terms of operation, this is the summation, this is the max. But we can still make use of the conditional independence to simplify the calculation. And this algorithm is called Viterbi algorithm. And here's the approach. So here, this is a max over n terms. So similar to that of some product, we can do it by iteration. We first calculate over the n minus 1, n minus 2, and then we can recursively do this and to simplify the calculation. So let's denote the quantity we want to calculate is J. And because the maximization of this is equal to the maximization of log, because this is a monotone function, and the maximization is equivalent. So we first denote which is the maximization of Z1 to Zn minus 1. Note that here we have Z minus 1, not Zn. And this, here's a log. And the J is equal to max of Wn, which is a function of Zn. And here, Wn is the quantity that we want to calculate out. And here's the summation of n minus 1 terms. We want to turn this Wn into some kind of recursive format so that we can calculate it out easily. So this Wn is equal to, okay, we can use n minus 1 is equivalent from z1 to zn. This is log probability of x1 to x n plus 1 at z1 to. And this maximization is over z1 to zn. Then here are some z n minus 1, n plus 1 terms. We want to separate these terms out because they are independent of this maximization. So this is equivalent to this is so this term is independent of z1 plus z1 to zn, so we can take it out. So this term is related to zn, so we can keep it. So this is equivalent to because this is a log, so the product here becomes the summation. So because this term is independent of z1 to zn, so we can separate out. So we need to do maximization over these terms. Since this term is only related, it's more compare these two terms. This term is only related with zn minus 1, so we can write it in this form, which is so this is actually omega Wn. So we turn this Wn minus 1 into some function of Wn. So we turn the original formula into some kind of recursive formula. So we can do the recursion. And the initial value is given here. So we can make use of this recursion to calculate out the most probable state. And this is called the Viterbi algorithm. Here we make use of the similar idea to that of the sum product algorithm. Because we make use of the conditional independence here, and we make use of the log. This log turns the product into the summation. So all the previous algorithms, sum product, Viterbi algorithm, they're conditioned on that we know all these parameters for a given model. So we know the transition probability, we know the initial probability, we know the emission probability, we know all of this. But in practical, most likely we don't know this probability. We want to use a hidden Markov model to model a practical scenario, practical application. And we want to learn all these parameters, all these transition probabilities, all these emission probabilities. So how are we going to do that? So one simple case is that one simple solution is that we use the maximum likelihood. We maximize the maximum likelihood over all the parameters. And this is the parameter selection process. So the goal is to optimize this marginal probability. This is the observed variable. We want to maximize the probability that we see this state by summation over all the possible latent variables. But this term is intractable. Why? Because for each Zi, there are k states, and there are n observed variables. So the total number of states is k to the power of n, which is polynomial, which is intractable. So the approach that we use to deal with this case is the EM algorithm. I think EM algorithm is mentioned in the previous recitation. So the main step of the EM algorithm is to maximize this modified objective function. Why do we want to modify this modified objective function? First, this is a more tractable version. The second, this is a lower bound of the original objective function. So this is a lower bound. Here we also put a log here. It's greater equal than Q. This is a lower bound of this one. And this one is much easier to calculate. So we turn to this. And there are two steps in calculating in the EM algorithm. First is the E step, which compute the Poisson distribution of the Z. After we compute this, given the old parameter, after we compute this, we fix this parameter, we fix this term. And then we maximize this whole term over the parameter theta. So this is the second step, which is called maximization step. So we first look at the first step, which is the E step. We want to calculate out the posterior distribution. Actually, we have done that by using the sum product algorithm and all the message passing, the procedure that we have done before. So first, I want to expand this term a little bit so that we can greatly simplify this. So we can expand this term because we already have the expression of the joint probability distribution. So this term is equivalent to, because we have a log here, so it becomes all the summation over n. This is the emission probability. This is transition probability, and we have the first term, which is the initial state probability. So this part is the second term. Is the second term. And we also have a summation in the first. And we have two summations. We switch the order of the two summations. Then for this part, we get since this only depends on Zn, the summation here is from Z1 to Zn. So we can ignore all those parts, which is independent, which has nothing to do with Zn. So it becomes this is a positive distribution of Zn we have divided before. So this is the first term. The second term, and this term has something to do with Zn and Zn minus 1. So we only need to keep these two terms. And then times and the first last one. So this is a positive distribution of Zn. This is a positive distribution of Zn and Zn minus 1 and Zn. This is a positive distribution of Z1. So these terms are exactly the positive distribution we calculated before here, which is a positive distribution. So this is how we make use of the sum product algorithm in calculating out the positive distributions. So this is the full expansion. And this is the positive distribution that we calculated out using sum product algorithms. So maximizing this is quite simple because we assume that the gamma, the parameters are all fixed. So we want to maximize this over the pi, over the a. So this is quite simple. We can directly take the derivative, set it to 0, and we can get the update rule. So these parameters are functions of odd values of a and pi. So we fix this, calculate out the a and pi, and then we recalculate these parameters, and we do iterations. And it will converge to some kind of fixed point. And then we are done in the optimization process, and we are done with the learning. So this is the EM algorithm for hidden Markov model. Okay, here's the main content of hidden Markov model, and you can try to implement the algorithm itself to do some practice. And you can also find some applications online, or you want to make use of this model in your research, you can do some practice. Okay, thank you.